Namaskar. Today we will discuss about pyroxene Hornfels facies. We have already discussed about Albite-Epidote-Hornfels facies and Hornblende-Hornfels facies. In continuation of that, the pyroxene Hornfels facies is a higher temperature as compared to Albite-Epidote-Hornfels facies as well as Hornblende-Hornfels facies. Pyroxene Hornfels facies content introduction, characteristics, minerals, features, mineralogical assemblages, important reactions, OSLO region, Norway, one example, physical condition of metamorphism, and conclusion. On the basis of pressure and temperature, we can divide the metamorphic phases into three types, mainly phases of low pressure, phases of intermediate pressure, phases of high pressure. Myasiro originally recognized three different phases series: a geolite, prehnite, pumpelite, blue schist, eclogite type, a typical Boravian type characterized by kyanite, Sillimanite type, and third, an Abukama type of green schist, amphibolite, gaulite characterized by paragensis, andalusite, Sillimanite type. The Abukama type is the name after the Abukama region in Japan and is similar to the Buchan type of the Dalindian. The phases of low pressure are listed below in order of increasing temperature of metamorphism. First, the Albite-Epidote-Hornfels facies. Second, Hornblende-Hornfels facies. Third, pyroxene Hornfels facies. And fourth, Sanidinite facies. If you will move from Albite to Sanidinite, the temperature of metamorphism increase from Albite-Epidote-Hornfels facies to Sanidinite facies. Pyroxene Hornfels facies are found in the innermost of some contact areoles. Their development is favored especially by shallow depths where pressure very low and proximity to intrusive of basic magma, that is gabbroic intrusions. Temperature is very high, nearly 1000 to 1200 degrees centigrade. Muscovite and quartz are no more stable, and cordierite and andalusite, Sillimanite coexist with K-feldspar. Biotite and Almandine garnet are of restricted occurrences. Mica and peltic rocks disappear by the reaction Muscovite plus quartz give rise to K-feldspar plus andalusite or Sillimanite plus water. Second reaction is Muscovite plus quartz plus biotite give rise to cordierite plus K-feldspar plus water. Further characteristic feature of this phases is absence of amphiboles. For example, hornblende, anthophylite, gaderite, cummingtonite, tremolite, actinolite, and occurrences of orthopyroxene, that is hypersthene and anisotite. In impure calcareous rocks, wollastonite is characteristic. Collectively, these distinguish the pyroxene Hornfels facies from the Hornblende-Hornfels facies. Winkler 1967 renamed the pyroxene Hornfels facies as the K-feldspar cordierite Hornfels facies based on this critical assemblages of peltic rocks. He demarcates the junction between potash-feldspar, cordierite facies and Hornblende-Hornfels facies by the reaction of breakdown of muscovite in the presence of quartz, as the transformation of amphibolite to orthopyroxene occur at temperature of 85 to 100 degrees centigrade above the breakdown of muscovite plus quartz. Winkler in 1967 subdivided the potash-feldspar cordierite facies into two subfacies, namely ortho-amphibole subfacies and orthopyroxene subfacies. Characteristics, mineral feature. Association of sillimanite or andalusite and cordierite with potash-feldspar in peltic rocks. Second, absence of muscovite and more restricted occurrences of biotite than in the Hornblende-Hornfels facies. Third, presence of diapsite, hypersthene and absence of amphiboles in basic hornfels. Fourth, presence of wollastonite in calcic assemblages and of calcite-forsterite-periclase and calcite-forsterite-diapsite in silica-poor dolomitic marbles. Fifth, Almandine garnet, when present, has a high Fe plus 2 plus Mg ratio compared with that of gamma-lite facies assemblages. The typical magnesium phases is cordierite. Stolite is unknown. If you will see the Hornblende-Hornfels facies and PYROXENE-Hornfels facies, and if we will compare also the PYROXENE-Hornfels facies with gamma-lite facies, usually in Hornblende-Hornfels facies we can see all the amphiboles are present, which are no more stable at higher temperature, and usually all the amphiboles are transferred into pyroxenes during PYROXENE-Hornfels facies, like breakdown of gaderite, anthophyllite and formation of your hypersthene plus inestatite, breakdown of your amphiboles, especially hornblende, can give rise to diapsite, hypersthene, plesioclase. And another thing, if you will compare with gamma-lite facies and PYROXENE-Hornfels facies, in both cases, one major difference is there. They usually show hornfelsic textures, while the gamma-lites show granuloblastic textures. Other mineral assemblages, except kyanite, garnet, etc., hypersthene, plesioclase are usually present in both cases. On the field, we can decipher or we can distinguish in both the gamma-lites as well as PYROXENE-Hornfels facies. PYROXENE-Hornfels facies usually associated with intrusive rock. They usually show the chill effect or thermal effect, so that if suppose you will move on outcrop, we can see usually the fabric change. If you will move towards intrusive body side, the fabric is entirely changed as compared to outer ridge. So, in this way we can decipher the pyroxene hornfels facies from gammalite facies. Please see the figure 1, 2 and 3 and 4 on the screen, that is ACF, AKF, AFM and CO, MgO, SiO2 as well as Al2O3, MgO and SiO2 diagrams. The important assemblages like peltic and quartzo-feldspathic assemblages. First is your andalusite, cordierite, quartz, orthoclase, biotite. Second is your plesioclase, cordierite, andalusite or sillimanite, biotite. Third is your plesioclase, cordierite, quartz, orthoclase, biotite. Fourth is your cordierite, plesioclase, hypersthene, quartz, potash-feldspar, biotite. The basic assemblages mainly plesioclase, hypersthene plus minus biotite. Next important assemblage is your plesioclase, diapside, hypersthene plus minus quartz. Next is your plesioclase, diapside, quartz. The important calcareous assemblages plesioclase, diapside, gracilorite, diapside, gracilorite, Vishwavidyalaya, and next important is your diapside, gracilorite, wollastonite. Other important assemblages mainly the silica diffusant assemblages. Please see the diagram on the screen, SiO2 CO MgO diagrams and Al2O3 SiO2 MgO diagrams on the screen. We can observe the following assemblages: calcareous assemblages, the calcite-forsterite-periclase and spinel, calcite-forsterite-spinel, calcite-forsterite-phlogopite, wollastonite, diapside, calcite, phlogopite and wollastonite, diapside, calcite, phlogopite. So, these are important calcareous assemblages. If suppose we will see the peltic assemblages as shown in figure Al2O3, MgO and SiO2 diagrams, we can observe the important assemblages, that is cordierite, corundum, andalusite, sillimanite, cordierite, corundum, spinel, hypersthene, cordierite, spinel and hypersthene, forsterite, spinel. The important reactions in the pyroxene hornfels facies are calcite plus quartz give rise to wollastonite plus CO2. Another reaction is your Mg anthophyllite give rise to anestatite plus quartz plus water. Mg anthophyllite plus forsterite give rise to anestatite plus water. Next important reaction is your magnesite give rise to periclase plus CO2. Another important reaction is dolomite give rise to periclase plus calcite plus water. Next is your gaderite plus quartz give rise to hypersthene plus cordierite plus water. Talc give rise to diapside plus anestatite plus quartz plus vapor. So, these are the important reactions mainly occur in pyroxene hornfels facies. If suppose we see the Oslo region of Norway, this was observed by the Goldsmith in 1911, account of contact metamorphism in Oslo district is one of the classic of petrology. The areoles are developed around small plutons of sodic cyanites and granites, where these cut Paleozoic, peltic, arenaceous and calcareous sediments. In most areoles, the assemblages of the pyroxene hornfels facies are confined to an inner zone that is flanked on the outer side of rocks of the Hornblende-Hornfels facies. From the stratigraphic evidence, Goldsmith computed that load pressure at the time of metamorphism as between 400 and 1000 bars. The OSLO paragensis is of special interest because it is a type of Ascola original Hornfels facies. Now the pyroxene Hornfels facies, Goldsmith recognized 10 principal assemblages. See the figure on the screen, ACF and Al2O3, MgO, SiO2 diagrams. Now we can observe the peltic and quartzo-feldspathic assemblages. First is quartz, orthoclase, andalusite, cordierite, biotite. Second is quartz, orthoclase, plesioclase, andalusite, cordierite plus minus biotite. Third is your quartz, orthoclase, plesioclase, biotite. Fourth is your quartz, orthoclase, plesioclase, cordierite, hypersthene. And now another important assemblages, that is calcareous, plesioclase, diapsite, gracilorite, Vishwavidyalaya. Another important assemblages is your diapsite, gracilorite, wollastonite, Vishwavidyalaya. And next important assemblages is diapsite, gracilorite, etc. It has been originally assumed following Goldsmith 1911 that gracilorite quartz is stable in the pyroxene Hornfels facies. This combination is common enough in calcareous assemblages of the Hornblende-Hornfels facies. Moreover, such assemblages as gracilorite, diapsite, plesioclase have not been reported in association with high-grade marbles. Calcite-forsterite diapsite, calcite-forsterite plesioclase in the inner zone of some areoles, but most such rocks contain calcite and are lack quartz, and although the grade of contact metamorphism is high, these gracilorite bearing assemblages are rare. If we found in close association with the diagnostic basic assemblages, plesioclase, diapsite, hypersthene, further ambiguity arises from the varied andradite content of metamorphic gracilorite and the albite content of even the more calcic plesioclases. Anorthite, wollastonite, the chemically equivalent assemblages to the gracilorite quartz, has long been considered. These are the characteristics of Sanidinite facies. Experimental investigation of the equilibrium gracilorite plus quartz give rise to anorthite plus wollastonite. That is indication of your breakdown of gracilorite, and gracilorite give rise to anorthite plus wollastonite. This reaction was carried out by Newton in 1966 at temperature 600 degrees centigrade, pressure nearly 2 kilobar. Supports the possibility that in the PYROXENE-Hornfels facies, the stable assemblages of pure phases is anorthite, wollastonite, and gracilorite quartz is no more stable. Andesine, wollastonite, diapside has been recorded in association with gracilorite periclase assemblages in high grade hornfels of certain facies. Harker in 1932, Carrick et al. In 1973. Third important assemblages is your basic, the periclase hyperthin plus minus quartz. Next important assemblage is your periclase diapside hyperthin plus minus quartz. Next important assemblage is your periclase diapside plus minus quartz. Pressure temperature condition for PYROXENE-Hornfels facies. The beginning of the PYROXENE-Hornfels facies is marked by the instability of the muscovite in the presence of quartz. Therefore, potash-feldspar plus cordierite and also potash-feldspar plus aluminosilicates can coexist in these phases. Further characteristic features of these phases are the absence of amphiboles, that is hornblende, anthophyllite, gaderite, cummingtonite, tremolite-tectonite, and the occurrences of orthopyroxene, that is anorthite and hyperthin. It would be expected that the formation of orthopyroxene on the one hand and the decomposition of orthoamphiboles and hornblende on the other hands would take place at the same condition at which the reactions muscovite plus quartz give rise to potash-feldspar plus aluminosilicate plus water. And another reaction is muscovite plus biotite plus quartz give rise to cordierite plus potash-feldspar plus water take place. Recent experiments have shown that this is not the case. Orthopyroxenes are formed at 85 to 100 degrees centigrade higher temperature depending on the pressure than those of the reaction given above, because this is the breakdown how the Hornblende-Hornfels facies change into PYROXENE-Hornfels facies. Thus, there is a fairly large temperature interval within the temperature range of potash-feldspar, cordierite, Hornfels facies, PYROXENE-Hornfels facies, in which orthopyroxene is absent and orthoamphiboles and hornblende are still stable. In other words, there is a temperature interval in which not yet all minerals assemblages discussed in the PYROXENE-Hornfels facies can be formed. Winkler in 1967 called the PYROXENE-Hornfels facies as the potash-feldspar, cordierite, Hornfels facies and subdivided it into the lower temperature orthoamphiboles subfacies and higher temperature that is orthopyroxene subfaces. The orthoamphiboles subfaces of the potash-feldspar cordierite-Hornfels facies differ from the Hornblende-Hornfels facies in that muscovite in the presence of quartz is no longer stable. The typical feature of the potash-feldspar cordierite-Hornfels facies, namely the coexistence of potash-feldspar plus cordierite and of potash-feldspar plus aluminosilicates applied to orthoamphiboles subfaces as well. Furthermore, in general, wollastonite will occur in place of calcite plus quartz because calcite at higher temperature change into wollastonite. If the temperature is increased beyond the temperature interval of the orthoamphiboles subfaces, potash-feldspar cordierite-Hornfels facies, orthoamphiboles usually becomes unstable in the presence of quartz or other minerals. At this stage, orthopyroxene is formed and orthopyroxene subfaces of the potash-feldspar cordierite-Hornfels facies is reached. So, in this way we can say how the potash-feldspar cordierite-Hornfels facies as well as pyroxene-Hornfels facies are similar and slightly different also. The mineral reactions leading to the formation of orthopyroxene provide data characteristics of the beginning of this subfaces. The following reactions has been studied. Reaction 1, gaderite plus quartz give rise to hypersthene plus cordierite plus water. Gaderite with intermediate FeMg ratio. This reaction was carried out at 665 degree centigrade at P water equal to 500 bars and 705 degree centigrade at P water equal to 1000 bars and 755 degree centigrade at P water equal to 2000 bars by Akela and Winkler 1966. Anthophyllite plus hornblende 1 give rise to orthopyroxene plus anorthite plus hornblende 2 plus water. Equilibrium data for a molecular replacement of 15% of MgO by FeO in the system. The reaction occur at 665 degree centigrade at P water pressure equal to 1000 bars and 665 degree centigrade at P water pressure equal to 2000 bars by Chaudhary and Winkler 1967. These temperatures are slightly higher than those of the previous reaction, that is the temperature range between 7 to 800 degree centigrade. The hornblende breakdown at very high temperature 800 degree centigrade P water pressure equal to 1300 bars and 1000 degree centigrade P water equal to 6000 bars. This reaction was carried out by Yoder and Telly 1962. Mg anthophyllite plus forsterite give rise to anesthite plus water. The temperature carried out by Ringwood 1963 at 745 degree centigrade 1 kilobar pressure. Mg anthophyllite give rise to anesthite plus quartz plus water at 745 degree centigrade at 1 kilobar pressure carried out by Greenwood 1963. These reactions suggest temperature of 700 to 750 degree centigrade for the beginning of the pyroxene-Hornfels facies. The upper temperature unit may not exceed 800 degree centigrade. The pressure condition ranges between few hundred bars to nearly 4 kilobars. The upper pressure limit is suggested by the common presence of andalusite, where P is less than triple point of aluminosilicate, absence of kyanite, common presence of cordierite, and very rare presence of your Almandine garnet, absence of garnet in peltic hornfels indicates pressure of less than 4 kilobars during pyroxene hornfels facies. The course content on the metamorphic low pressure facies begin with the introduction, followed by the description of the pyroxene hornfels facies. The important characteristics minerals in this facies, the chemographic phase relationship with the help of ACF, AKF, Al2O3, MgO, SiO2 and CO, MgO, SiO2 diagrams, and the mineral assemblages for the peltic, basic, calcareous and silica deficient rocks, and finally the physical condition of metamorphism during pyroxene hornfels facies.